Hello, I am Alexandra Ashly M. Olsem, taking ECEA 111, Section EO2 under Engineer Marian. And this is my coursework. Today we'll be talking about angular modulation and specifically on frequency modulation and phase modulation. Frequency modulation is a modulation in which frequency of the carrier wave changes according to the instantaneous amplitude of the modulating signal, keeping phase and amplitude constant. Frequency of the carrier wave is modified in order to send the data or information. It cannot transmit over long distances, have a small. Its modulation index is always greater than 1. And in frequency modulation, amplitude and phase remain. On the other hand, phase modulation is a modulation in which the phase of the carrier wave changes according to the instantaneous amplitude and the frequency constant, and the two modulations are similar, but in phase modulation, frequency of the carrier signal um, is not increased. Phase modulation is used in mobile systems. The phase of the carrier wave is modified in order to send the data or information. So here the comparison of the AM, FM, and PM modulations. So we can see here the definition of the three. Frequency modulation is a technique of modulation which the carrier varies in accordance with the amplitude of modulating signal. Amplitude and phase constant. Same with the AM here, and also the PM. Now with the noise, immunity of FM is superior to AM and PM. AM are very susceptible to noise, and noise immunity better than AM but not FM. Yung which are the phase model. And for the functions, here the frequency of the carrier wave deviates for the voltage of the modulating signal input for FM. For AM, the amplitude of a carrier wave in AM diverges as per amplitude or voltage of modulating signal input. And for the PM, phase of the carrier wave varies as per the voltage of modulating signal input. We have the constant parameter and so this is what an AM modulated signal is like, as well as for the PM and the FM. So for the frequency modulation, we can summarize it to this equation, frequency domain, and also the time domain. Now we have phase modulation, and we can see the mathematical equation, as well as the frequency domain and the time domain. For this summary of the FM and PM, the mathematical representation of frequency modulation consists of sinusoidal expression with the integral of the baseband signal added to the argument of the sine or cosine. Second, the modulation index can be used to make the frequency deviation more sensitive or less sensitive to variations in the baseband value. Third, narrow band frequency modulation results in a translation of the spectrum of the integral of the baseband signal to a band surrounding the carrier field. And last, an FM spectrum is influenced by the modulation index as well as by the ratio of the amplitude of the modulating signal to the frequency of the modulation. And I think we have four more. The phase modulation is calculated by adding the baseband signal to the argument of cosine function that represents. Second, the modulation index makes phase variations more or less sensitive to the behavior of the baseband signal. Third, the frequency domain effects of phase modulation are similar to those of frequency modulation. Fourth, analog phase modulation is not common. However, digital phase modulation is widely. So, from the second part of this discussion, wherein we have the examples in solving parameters. For the FM, and PM modulation index, we have two problems here. First, FM modulator uses a modulating signal with an actual frequency of 50 kHz and an amplitude of 4.5 volts. If the modulator's deviation sensitivity is 80 kHz per volt, find the modulation index. So we use this equation for the frequency modulation, where K2 times Vn over Fn modulate. Okay. Here we substitute the values of this to the ones given in the problem. We have the deviation sensitivity of 80 kHz times 4.5 volts a Vm over the actual frequency of 50, and that arrives at 7.2 for modulation index. And for the phase modulation, a PM modulator has a sensitivity deviation of 2.5 rads per volt. If the modulating signal voltage is 4 volts and 40 kHz, effectively determine phase modulation. For that, we use this sensitivity deviation 2.5 rads times the frequency or the signal voltage of 4 volts. That would be 10 rads. Next, we have the FM PM percent modulation. So a PM signal has a maximum allowed deviation of 12 kHz and an actual deviation of 7 kHz. What is the percentage modulation? So basically, for us to get the percent modulation, we get the actual frequency over the maximum allowed deviation, which is 12 kHz times 100. 7 kHz over 12 kHz times 100 equals 58.33%. Now, for the frequency deviation for FM and phase deviation for PM, two problems. Determine the peak frequency deviation for a FM modulator with a deviation sensitivity of 10 Hz per volt and a peak modulating signal of 5 volts. Frequency deviation, this is our equation. We substitute K2 is the 10 kHz, that would be the deviation times the peak modulating signal, the 5 volts, that would be 50 kHz. And for the phase deviation for PM modulator has a sensitivity deviation of 5 rads if the modulating signal voltage and frequency 4 volts and 4 kHz effectively determine the phase deviation. Same as the first problem we had the other slide. Last slide, so we got the modulation index of 10 rads for PM, and using that we multiply that one to the frequency of 40 kHz 400 kHz. Now for the deviation ratio, FM modulator is a modulating signal with an actual frequency of 50 kHz and an amplitude of 4.5 volts. If the modulator's deviation sensitivity 80 kilohertz for both time the modulation. Same with the first problem. So dr is said to be equal to the modulation index of 7.2. So we arrive at same answer of 7.2. Second, for the PM modulator has a sensitivity deviation of 2.5 rads per volt if the modulated signal voltage and frequency is 4 volts and 40 kilohertz respectively, determine the phase deviation rate. With the one that we have earlier of 400 kilohertz, we divide this one to the actual frequency of 40 kilohertz, right at 10, or DR, deviation. Lastly, we have practical bandwidth or FM. So if the maximum frequency deviation of the carrier is positive or negative 12 kilohertz and the maximum modulating frequency is 2.5 kilohertz, the modulating index is here. We use this formula. Same as the K2 VM, K2 times VM over FM. But we use this FD over F. That will be equal to 12 kilohertz over 2.5 kilohertz. That would be equal to 4 modulating it. And using this, or rather using these values, we can compute for the bandwidth. So that is just 2 times the sum of the maximum frequency deviation and the maximum modulating. That would be 2 times 12 kilohertz plus 2.5. That would be equal to 29 kilohertz. So here are the references. And thank you and stay safe.